Thank you. Thank you. Thank you. So this is John work with Xu Guang in Beijing University. So today I would like to talk a little bit about the geometry of related to scalar curvature. So of course scalar curvature is very weak. But we still can say something. So one of the, well, the typeset is not very good. Okay, anyway, suppose we are talking about some asymptotically flat manifold. So near infinity, it just looks like Euclidean space. Let E be an N, so an N, so just like a Euclidean space minus some ball. Then we can define the so-called ADM mass. ADM mass defined for this N defined in this formula. So where Gij is the metric in terms of the Euclidean coordinate. Okay, the coordinate. And of course, we assume this is so-called asymptotically flat. That means near infinity is look like delta Ij. Gij look like delta Ij. Then we look at this quantity and take the limit. Then this is called the ADM mass of this N. Probably it should be called the energy. So because we are thinking about what? We are thinking about a so-called space-like surface in a space-time, which is time symmetric. That means the second fundamental form is 0. Suppose the second fundamental form is 0, then we can talk about, usually we can talk about the energy and the linear momentum. But if the second fundamental form is 0, then we have only the energy. So the mass is the norm as a vector. The energy together with the linear momentum as a vector in the Minkowski space, you take the norm. So that should be non-negative. So that is the so-called mass. But here is maybe we just call it this energy, but I still call this mass in this talk. So, well, it's well known that in 79 and 81, they proved the positive mass theorem, Sheng and Yao. So they proved that if the scalar curvature for an asymptotically flat manifold is non-negative, only non-negative, then the AD mass should be non-negative also. Okay. Well, if it is 0 for one N, because the manifold may have several N. So, but if for some N the mass is 0, then it should be a Euclidean space. M itself is Euclidean space. The result can be generalized to N from 3, the dimension from 3 to 7. So the reason for this dimension is that in their proof, they use the minimal surface. So they construct certain kind of minimal surface, and which is area minimizing. And they use the second variation formula together with all kind of conditions to get some contradiction. So the scalar curvature non-negative just come from the fact that suppose, as in the previous talk, suppose you look at the Einstein equation and you look at the right-hand side, which is the energy momentum tensor. That means the material. So if the energy momentum tensor satisfies the so-called dominant energy condition, and suppose we have a time symmetric, or even if it's maximal, that means the mean curvature is 0. Then by the Gauss equation, we can conclude that the scalar curvature should be non-negative. That is the reason why we are interested in this part. Okay. So of course, if you use Spinner, Witten, he proved that this is actually true for spin manifold, for space-time also. So there's a space-time version And Bartlett also proved this for the reminding case. Okay, so, but for this theorem, so we just assume the scalar curvature is non-negative. But for this theorem, in some case, if the metric is not smooth, then in some case we still have this kind of result. That means the mass is non-negative. So for example, Lee, he proved that if we have a metric, the metric is ellipsis, which is very, very nice outside certain set. The set, the dimension of the set is less than or equal to n over 2, where n is the dimension of the manifold. So when we say that the dimension is less than or equal to n over 2, maybe we just think of this as an embedded submanifold. Okay, but of course we can look at it. We can discuss this a little bit more detail later. Okay, suppose this is true, or maybe n less than 8, or it is spin, then we can show that. Another assumption is that suppose G naught in certain kind of solar space, and the dimension of sigma is less than some constant, then the positive mass theorem is still true. Okay, here G naught is ellipsis, all right, and it has C2 non-bound outside sigma. Okay. So later on, this can be generalized to the case that G, the metric is in C0, intersect this set. Well, before Lee, Mel has proved the following things. So here the dimension of singular set is small. Here the dimension of singular set is large in the sense that it's an embedded hypersurface. Well, he assumed, Mel assumed that the metric is ellipsis. So we have a compact set. We have a compact hypersurface, sigma. So the metric is smooth here, up to the boundary. And it is ellipsis continuous. That means restrict on the boundary, they are the same. But there may be so-called some kinds, there may be some corner, so you just throw it. There's some corner. Well, we cannot just assume G naught is etc. If the dimension is small, then we can just assume this. However, if the dimension is large, just like this, then there's another assumption. Okay, the assumption, say for example, if sigma is an embedded hypersurface in M3, and locally is a, so this is a correlation. So T equal to 0 is sigma. So sigma is T equal to 0. Then this is T bigger than 0. This is T less than 0. Say, for example, you can write in this way. Suppose you can write it this way, and ddt has unit length in both metric, so G plus and G minus. Notice that the ddt may not be smooth because it's not a smooth metric. Then, in this case, let us assume this is smooth. Then we can use the second variational formula to get the derivative of the mean curvature. And then we use the Gauss equation and then write down the scalar curvature of the big manifold. And this can be written in terms of the Gaussian curvature, the second fundamental form, and the mean curvature, together with the derivative of this one. Okay. So if you want the left-hand side to be non-negative, so you just integrate from, say, for example, S, from just along a curve here, say, for example, minus epsilon to epsilon. This should be non-negative, okay? Or if you want, you just multiply certain kind of non-negative cutoff function. This should be non-negative. Then you just integrate this. Well, because everything is nice, therefore when you integrate, let epsilon go to 0. You got 0 here. You got 0 here. You got 0 here. You got 0 here. Because everything is bounded, except the last part, if it is not smooth. Therefore, if sigma is a singular set, then if you want S to be non-negative, you better have the following condition. Suppose you have a mean curvature, H minus here, and H plus over here. The mean curvature are not the same. Then, when you integrate, therefore, you one subtract another one, therefore, we need this condition. So, under this condition, together with the previous assumption, then Mel proved that this positive mass theorem is still true. So actually, C and I also proved this for the case that the mean curvature are the same, but for the spin manifold, because we encounter some problem related to this kind of stuff. So later on, well, I'm sorry that I'm very bad at pronouncing people's name. I don't know how to pronounce them, but these two persons, all right, to be neutral, prove that Mel's result using the Ricci flow. So this, so it has something to do with Ricci flow. So therefore, it's nice to talk about this topic in this workshop. Okay. Then some more results. Lee and their Froch. For spin manifold, they prove, just forget those kind of condition, all right? Condition. But this condition also already implies all previous results for the spin manifold, because in their proof, they also use Witten's method. Okay, so let us go back and take a look about this condition. So you look at the metric on the Euclidean space. This is the Euclidean metric. You take a conformal factor where M is positive. M is positive. Of course, this metric is only defined for R big enough, R bigger than 2M. For this metric, if you compute the scalar curvature, well, this is in R3, so you compute the scalar curvature is 0. It's 0. And M is bigger than 0. Okay? Well, this is asymptotically flat near infinity at least. But the mass is exactly equal to minus M, which is negative. Minus M, which is negative. So let us look at this example. So we have a metric outside certain ball, R equal to 2M, outside certain ball. Okay, we have something like that. All right, so you just take a ball, a coordinate sphere. Take a coordinate sphere, therefore, we have two metrics. The first metric is the Euclidean metric, the second metric is the metric G. For the metric G, we can compute this mean curvature to be this. Well, for the SR with the metric G, this is also a sphere, but the radius is not R. Therefore, if you consider this SR, this SR as a, together with the metric G, as an embedded surface in R3, then the mean curvature is this one. Therefore, if you forget this part, we cannot define the metric in this part. This is our original metric, and then we combine this metric together with a ball in Euclidean space here, with the reasonable I mean the appropriate radius, then we have a metric which is not smooth, which is only ellipses here. And then the mean curvature does not satisfy this condition. So in this case, the mean curvature, you can see that H minus is less than H plus, but the mass is negative. Therefore, in Mel's result, you need the mean curvature property. Okay. So
when we talk about positive mass, is the matrix supposed to satisfy the Einstein equation in the interior?
yeah, but you have the right hand side, you have a tensor. We don't know what is a tensor. What is a tensor? But in this case, we just have time symmetric case. So the second fundamental form is 0. Okay. So we just write down the energy condition and get some condition on the scalar curvature. So in Hawkins' book, he said, well, Einstein equation is very easy. It's very easy. You just write down R alpha beta minus 1. Vacuum, all right? R. You take any metric, you just write down this. And then you say that this is just T alpha beta. And this is the Einstein equation. You can always do that. So, but it is meaningless, right? It's meaningless. So therefore, you should have some assumption on the right-hand side in order to get certain information. So in the previous case, we are talking about asymptotically flat manifold. How about scalar curvature and compact manifolds? There are many results, of course. I'm not an expert. I have done very little in this direction. But let us just mention what I know. So in the same year, because they just use the same technique basically, but of course it's quite different. That means they use minimal surface. Therefore, in almost the same time, they prove that, or maybe before the positive mass theorem, they prove that if G is a metric on the N torus with non-negative scalar curvature, if the dimension is less than 7 because they use minimal surface, then G must be flat. So this is also true for all dimensions, proved by Gromov and Norton. Okay. Well, because of this fact, so we would like to, because of previous result for metric, for positive mass theorem for singular metrics, so we would like to understand if there anything about compact manifold related to scalar curvature, so that the metric may not be smooth, So that is what we want to study. So in order, say for example, if we have certain kind of metric on the torus, and the metric may not be smooth, but the scalar curvature is still non-negative, can we say that G is flat? Okay. Well, we would like to discuss another problem. When we solve the other problem, then we can solve this. The method. So, what is the question we have in mind? So let us recall the so-called Yamabe invariant. So we have a rebinding metric on a compact manifold, smooth compact manifold. Therefore, the smooth structure is fixed. We have a smooth manifold. And then we have a conformal class on metric G. For this conformal class, we have a Yamabe constant, C. This Yamabe constant, basically, is just the infimum of the scalar curvature if the volume is normalized to be 1. Okay. So then we can take all the conformal cars. And take the supremum. Then this is called the Yamabe invariant. Also, this is also called sigma invariant by Ricci. Well, we know that sigma m is finite because sigma n is always less than the sigma of n sphere, which is the right-hand side. I mean this part. Okay, and well, if sigma m is non-positive, then we have certain kind of nice property. That means if G realized, usually we may not have a metric, so that it just realized the sigma m. Okay, but suppose it realized sigma m, then G must be Einstein. Okay, if sigma m is positive, then this may not be true. We don't know what is the general situation. Well, we want to discuss this problem. What can we say if G may not be smooth? So, suppose we have a smooth manifold, and then M, then we can define sigma M, and then we have a metric G, so that G may not be smooth, but the scalar curvature satisfies certain kind of property. Then what can we say? So, well, first, we consider the case that the singular set has codimension at least 2. Well, we have the following property. If sigma n is non-positive and G naught is a continuous Riemannian metric so that the volume is 1. First of all, it satisfies that there's a compact set sigma. Outside sigma, G naught is okay. And the scalar curvature is at least sigma m. Okay. Secondly, G naught is in certain kind of sober space where Q is bigger than n. I don't know whether one can solve this problem for Q equal to n. Okay. So, in particular, G naught is held up. Well, we say that the codimension is at least 2 means that you take any epsilon. Because this is a Riemannian metric, therefore we can talk about the distance function. You look at this distance function, look at this set, and then the dimension is at least 2 means that the volume of this one is less than or equal to some constant times epsilon squared. C is a fixed constant. Well, if M and G naught satisfy this condition, then G naught must be Einstein outside the singular set. That is what we want to prove. Okay. So in order to prove this, it's the idea is straightforward. You just approximate by smooth metric. Okay. The first approximation is just by some modification. So let us assume G naught is as above. Forget this one. Well, let us assume sigma, the compact set, is contained in some coordinate neighborhood. And then on this neighborhood, the metric is almost like the Euclidean metric. Then, if epsilon is small enough, we can find a function so that rho equal to epsilon in the neighborhood of sigma, outside an open set minus outside and sigma 2 epsilon, then rho is 0. Okay, the gradient is bounded, the second derivative is bounded by C epsilon minus 1. Okay, so that is we can find such a function, smooth function. So we just use the distance function, etc., and then use modification. Then we just take a non-negative function, just modifier, okay, and then epsilon, if psi be a cutoff function, so that is if psi equal to 1 near sigma, if psi equal to 0 outside the coordinate set. Then we have the first approximation. So G epsilon 0, ij as a function is defined in this way. If psi is a cutoff function, this is a nice function, and then x minus Well, if rho x is just a constant, it's just the ordinary modification. So here we use rho x. I think this idea just comes from Mel, at least, as far as I know. And then define another metric, which is G epsilon. Near U, near sigma, we have G epsilon 0. Outside sigma, we have 1 minus epsilon, G 0. So therefore, we have G 0. And then now we have G, or maybe 0 epsilon. Yeah, G epsilon 0. So this first approximation, the lemma is that one can find such a lambda which is small enough so that this is a nice metric. This is a nice metric, and then this one converts to G0 in C0 norm only. And of course, outside, certain part is equal to G0. And moreover, because initially the first derivative of G has some bound, the LP bound. This is also true, independent of epsilon. Okay. So now, next we have another approximation. So we have first approximation. We have G0, we have G epsilon 0. So this will converge to this one uniformly. Okay, uniformly. Well, in particular, G epsilon 0 and G epsilon 0 epsilon pi 0 are very close to each other. Okay, then we can use a result by Miles-Simon. So we just look at the determined Ricci flow. Ricci flow. Okay. It's given by this one. Okay. So H is a certain background metric. So, well, we still call this H flow as in the work of Miles-Simon. And he proved the following. There exists an epsilon n bigger than 0, only depend on the dimension, such that if this is a compact or non-compact manifold, doesn't matter. But this is very close, this epsilon, very close to a smooth, complete Riemannian metric H with bounded curvature. Then the H flow, the determined flow, Ricci flow, has a smooth solution up to some time t. And also we have certain kind of estimate for the metric G. Okay, it is important that the time t, the interval, depends only on n and the background metric. So this Ci also depends only on n and the background metric. That is the most important part. So if this is true, then because G epsilon and then G epsilon pi are very close, therefore we just fix some small epsilon 1, and all the rest are very close to this one. Of course, this one has bounded curvature, therefore you can solve the H flow. This is H, solve the H flow up to a certain time, and then we have certain kind of estimate. Here. So say, for example, when the derivative is first derivative, it should be less than or equal to C over T. The square is less than C over T, okay? For example, okay, however, if initially the gradient of the initial metric has bounded is ellipsis, then we also have this one. Okay? And in general, we only have also the second derivative also satisfies this one. Okay? So, we can assume the metric G naught is ellipsis, therefore it satisfies It satisfies this one. Well, but usually we just try to do it as general as possible so that people will be confusing. So therefore we just assume a little bit. Then suppose we have G, I mean the metric here is only C alpha. Then one may expect that this is the derivative square will be less than or equal to some constant t to a certain power. This power is less than 1. That is what we want to do. Okay, so that is the case. All right. So, well, consider this approximation G0. So then we have, in our case, the first approximation. The second approximation, we have G epsilon t. So from here, we solve the equation. Well, for this G epsilon t, we have certain property. The first property, as I mentioned, because we assume this, in some sense, is held, therefore we have such kind of estimate, such kind of second-order estimate. In particular, the curvature satisfying this kind of property. Okay? Well, because this initial data are smooth, therefore we can transform it into a Ricci flow. Transform into a Ricci flow, therefore we can use the equation for the scalar curvature. So if initially the scalar curvature is bounded below by sigma, then of course when you take the Ricci flow, the scalar curvature is still bounded below by sigma. However, this metric, the scalar curvature may not be bounded from below. Therefore, what we get is only this one. So this one times that one is non-increasing in this region. So delta is less than 1. Therefore, this is nice. So what is GT? Because of the result of Simon's, therefore we have certain kind of convergence. Therefore, this will converge to some GT here. This is also satisfy the H-flow equation. So for this one, we have this inequality. It's quite not so difficult to prove. Just make it, just look at this term more carefully. Just use the integral form of the derivative of the scalar curvature, the negative part. So, well, when you differentiate, you end up with some scalar curvature come out. However, the scalar curvature is just the second derivative of the metric, which has some estimate. Therefore, we have this. And next, up to now, we do not use anything about the size of the singular set. So if the size of the singular set is small, then one can prove that this is actually go to 0 when t go to 0. Okay? So therefore, as t. So the first thing is that we have a GT here. GT, the scalar curvature of t, is still bigger than or equal to sigma. So this is bigger than or equal to sigma outside too many sigma, outside the singular set. But this one is bigger than or equal to sigma everywhere. It is smooth. Okay. So a first result is that from this argument, we know that suppose the manifold is a torus, n torus, then it satisfies certain kind of condition as mentioned above. Then with sigma m is equal to 0. Okay. Suppose we have applied the previous result for sigma m equal to 0. Then suppose the initial metric has non-negative scalar curvature outside the singular set, then we can construct a family of metric on the sigma n, okay, on the torus, so that the scalar curvature is still non-negative. Therefore, we can apply previous results to show that the GT must be flat. Then let T go to 0. Other than at this singular set, everything is okay. The convergence is okay. Therefore, initial metric should be flat away from sigma. So that is the proof for this particular case. But we want to understand what is G0 in general. Okay? So the question is that, so remember what is sigma m? Sigma m is the supremum of the Yamabe constant of some class, or the class. Well, this is just the infimum of the scalar curvature normalized with this one to be 1, all right? Suppose the volume of GT is 1. Then, because of this fact, because of previous result, sigma m is non-positive, therefore GT should be Einstein. Therefore, you take the limit, it should be Einstein. But the point is that because you change the metric, therefore the volume may not be 1. May not be 1. Therefore, we still have to do something. Technically, we still have to do something. So, well, if in our case, then we have a GT, we just let Ti go to 0, therefore we have a sequence of Gi, and then we just normalize the volume to be 1. However, the scalar curvature may be sigma m minus something, where delta I go to 0. Delta I go to 0. And then we would like to get some information. Well, then we prove the theorem. The theorem said that outside the singular set, it should be Einstein. That means the traceless part, traceless part should be 0. So therefore, we just take the traceless part of the Ricci, of the initial metric. This should be G0, the initial metric. So you look at this, and you look at the linearization of the scalar curvature at the smooth point. It is given by this one. If H is the perturbation tensor. In our case, suppose we just take H to be this one, say for example. Then the trace is 0, therefore we don't have this one. If the trace is 0, then we don't have this one. Then we still have this one, we still have this one. But the trace is 0, therefore this can be replaced by the traceless part. Okay? So, therefore, because it's infimum of the scalar curvature, when you take the derivative and you use derivative of the scalar curvature along certain kind of direction, H direction, which is related to this one, then we have some sign over here. Therefore, it's either increasing or decreasing in certain direction. Then we would, maybe we have some contradiction. But the metric is not smooth everywhere. Therefore, we just take a cutoff function. Suppose at some point away from the sigma singular set, then we just take a smooth function. A smooth function, okay, and then multiply this function by this tensor. Okay, use this perturbation. Originally, it's Gi. So we have something like that. So here is the Gi. So this is G0, the original metric. Then we have a GT here. So we just take Ti go to 0, therefore this is Gi, which is equal to GTi, where Ti go to 0. So Gi satisfies some property. Well, this one has a scalar curvature bounded below by something. Then we just change a little bit tau. HI. Okay. So call this new metric perturbation. Okay, perturbation, and then by the solution of the Yamabe problem, you can always find a smooth metric which is conformal to this one, so that it satisfies. The conformal factor satisfies this condition. Okay. What is lambda? Lambda is just the Yamabe constant for the conformal class of this one. Okay. Therefore, we have to normalize. Okay. First of all, sigma m is the supremum. Therefore, lambda I tau should be less than the sigma m for any tau, small. Okay. And V I tau, the volume, is, as I said, we have to be careful about the volume. But fortunately, the volume here is very nice because it's just 1 plus order of tau squared. Why this is true? Because the variation of the volume just given by the trace. But this is traceless. That means the first derivative is 0. Therefore, we have second, only tau squared. Okay. Then using this equation and multiply by u, okay, and then integrating by parts, we have this kind of inequality. It takes a while to get this. It's not that complicated, but we need certain kind of argument. So here we use the fact. So we just go back to the equation. We have scalar curvature over here. All right. So, but the scalar curvature is different from the scalar curvature GI. We have some perturbation. We cannot just use the first variation because it only gives you the first derivative. But tau may be positive somewhere. Okay, tau may be non-zero here. So we have to keep track of the order of tau. Therefore, we need other things. So S I tau is equal to the scalar curvature of GI, which is bounded below by sigma m, and then the divergent part, because the trace is 0, but the divergence may not be 0, because you have a cutoff function in front, and then we have this part. Okay. So therefore, finally, we have this inequality. Well, this goes down to 1 plus tau squared, and this one is less than sigma. Therefore, we will have a contradiction if we first choose tau k tends to 0, and then we choose delta I k less than or equal to tau k squared. So this one is small because everything is independent of I and tau. Then we can prove that. And finally, we prove that this one is bounded below. Therefore, the right-hand side is negative and the left-hand side is positive. Then we have a contradiction. So that is the proof of the result. So in case sigma has codimension 1, we just follow the method by Mel and then get this part. Suppose the codimension is 1, then G0 is still Einstein outside sigma, and the mean curvature should coincide. If it satisfies this condition, sigma is an embedded surface, etc., and the mean curvature should satisfy certain kind of condition. Okay, so here I have to say a little bit about the assumption B2. So in Mel's original result, so he just assumed that in this part we have a tabular label, and this part we have tabular label. Well, T may not be smooth. Here we assume T is smooth because I don't want to change the smooth structure of the manifold. So, and then we have the crucial inequality. The mean curvature should be bigger than LB. Okay, so then we still have this kind of property. So the question is that in this case, if G naught actually is smooth. So suppose we assume G0 is ellipsis, then one can use the harmonic coordinate. One can solve the harmonic coordinate equation, find the harmonic structure, and then write down the Einstein equation, and then get some more information to show that G0 is smooth. Okay, so if it's ellipsis and smooth outside that one, then actually we can have a smooth metric, except the smooth structure is changed, already changed. Okay, already changed. So I would like to mention that for the time being, up to now, we only proved two cases. The codimension one, the codimension one, codimension of sigma is at least 2, or codimension 1 case. But in between, I don't know how to handle this. In between, I don't know how to do this. Here, for this particular result, so it's still okay in between. So we just use harmonic coordinate. I don't want to go through it. Many of you already know. But the technique can be used to prove a positive mass theorem for dimension n less than 4 without the spin condition. Okay. So I won't state the theorem because it's rather technical. So finally, I would like to introduce some example. So you look at the metric, which is a cone-like metric, and then you compute the scalar curvature. The scalar curvature is given by this one, away from the cone vertex. And we know that S is bigger than 0 if R is small and beta bigger than 1. And then we are interested in S bigger than 0, where beta equal to 1 and alpha is less than 1. Beta is equal to 1, that means this is R squared. Alpha is less than 1, that means the angle is small. The angle is small. And another case is that this is also true. If beta is between less than 1, but is between 2/3, etc. Okay? So what is that means? Because I would like to introduce another example. So you just consider the Euclidean metric multiplied by this conformal factor when m is bigger than 0. Well, of course, R should be big. Near R equal to 2m, if we set rho to be this one, then the metric can be written in this way. G equal to d rho squared times C times rho to the 2 beta times something. This is standard metric where beta is exactly 2/3. Okay? So in this case, the positive mass theorem is not true. So the point is that for a cone singularity, so in the previous result, we always assume G0 is continuous. But if G0 is not continuous, if we have a cone singularity, then sometimes we have positive mass theorem, sometimes we do not have a positive mass theorem. So up to now, I still don't know how to handle the general case because it's quite interesting to see if we have a cone singularity in more general sense, not like this. Okay, can we get under what condition we can get a positive mass theorem? Okay. Maybe I stop here. So, thank you.
When the metric is not continuous, the energy momentum tensor is a delta function or distribution. But you can still put some inequality, positivity condition. So is that helpful
locally
for positive mass?
Well, that is what I want to understand. So I don't know how to, because we have example, we have positive. mass, but we have non-positive mass. But I don't know what is the general situation. And also, this is quite special. I don't like this example.
Yeah, but the energy momentum tensor, as a distribution, it has a sort of.
Yeah. You still
it's
can say that this is positive. Yeah. No?
You said you didn't want to show us your theorem, but could you put it up anyway?
Pardon?
Could you put up the positive mass theorem that you proved?
Oh, you mean the statement?
Yeah, you said you didn't want to show us, but I'd like
Because two, it's a little bit messy. So the same. So this kind of is rather technical. Why I do that? Because I only can find for smooth manifold. Forget everything here. Suppose for smooth manifold, I only get a positive mass theorem in the reference of this form. How should be big? So therefore, in the smoothing procedure, we have to show that the GT, the smoothing metric, should satisfy this kind of condition. That is the more difficult part. But it is okay. Okay, thank you.